All right, so we're going to finish up Chapter 14 today with one more really big idea and then a little bit more practice with our probability questions. That last big idea is called the law of large numbers. Now here's our definition from the textbook. Definition says the long-run relative frequency. Remember, long-run relative frequency is just your probability. Okay, we've seen that before. So our probability of repeated independent events. Independent events, we saw, are events where one outcome does not affect another. The most common example we talk about is flipping a coin. Okay? Flipping it one time doesn't change probability for the next coin flip. And repeated, we're going to do it lots of times. Okay? So we're going to repeat this idea. It settles down to the true probability. So it's going to get closer and closer and closer as the number of trials increases. So the more we do it. So our probability, okay, what we're observing here, right? That's kind of an observing. The probability we observe when we do something over and over again gets closer to the true probability as we do it more often. So again, the most common example we talk about is flipping a coin. We say that the probability of getting heads is 0.5, right? Half, 50-50. But if you were to flip 10 coins, it wouldn't be unusual to see 6 heads. That's because we're not doing a large number of trials. But if we did this over and over again, okay, repeated, as the number of trials increases, if we did this 10,000 times, we'd get a lot closer to half heads. And that's this idea. This is not a law of averages. So common misunderstanding about probability is kind of this idea. Well, I'm flipping a coin and I get heads. And then I flip it again and I get heads. And then I flip it again and I get heads. Now, this is a fair coin. Okay? Weird things can happen. I flip it again, I get heads. I flip it again, I get heads. Now, if that has happened and I ask you, what's the probability the next coin toss is heads again? You should still say 1/2, right? Nothing has changed. But there are these silly people who say, well, by the law of averages, we're due, I love this, we're due for a tails. So they're like, oh yeah, the next one's not going to be heads at all, it's going to be tails. This is preposterous. This is like saying that coin somehow has a memory. And it remembers that it's given you way too many heads and now it needs to give you a tails. Okay, this is, okay, bogus ideas, okay, bogus ideas. Here and here and here, okay? Coins don't remember what's going on, so there's no law of averages. Just as an example of like real life, people think there's a law of averages. There was a casino in Monte Carlo, so I marked that on the map for you here. That's where Monte Carlo is in Monaco. And they were playing this game called roulette. Here's a picture of a roulette wheel in case you haven't seen that before. And you're really choosing between black and red. There's like one green square. You can't even see it on that picture. So it's almost like flipping a coin, almost 50-50. And true story, they're playing this game, and the little ball goes around the wheel, and it landed on black 26 times in a row. Crazy weird. Around the 15th time, people started betting on red like crazy because it was due. Okay, it was overdue. That was, they were trying to use this law of averages, and it doesn't exist. As you can see, they waited around from the 15th time to the 27th before they saw red. Okay, so don't get caught in this bogus idea that just because something weird happens that it's due for the other outcome. Okay, it doesn't work that way. All right, so let's switch gears and go back to some actual story problems about our probability questions. I'm going to make them just a little bit more complicated this time, but I'm still going to use the same story problems we've looked at previously. So this is one where we're talking about car manufacturing, and 40% of cars are from the US, 30% from Japan, 10% Germany, 20% from just other countries. And we're going to select multiple cars at random. So the first question says, none of 3 cars come from Germany. So something that I like to do when we get into multiple cars is I kind of draw myself like a little picture. And these are actually and questions because we're talking about 3 cars. So it's car number 1 and car number 2 and car number 3. Here's my little shorthand symbol for and. So the first car, let's see, none of the 3 cars come from Germany. So this first car, it is not from Germany. The second car, well, none of the 3 cars can come from Germany, so the second car is still not from Germany. And the third car is not from Germany. So if I just put some probabilities with this, this really, I could write, is the probability of a car not from Germany, and probability of the car is not from Germany, and the probability of a car is not from Germany. So let's put some numbers in there. Let's see, not Germany. Well, Germany is 10%, so not Germany, if I use my complement rule, would then be 90%. Or again, I like to use decimals so much more. I make less mistakes that way. So I'm going to use 0.9. So this is going to be 0.9. Remember, and tells us to multiply. I'll just put parentheses. I don't want to get confused with all my little dots here. And not Germany. And not Germany. So what I have here is 0.9 to the 3rd power. If I plug that in my calculator, I get 0.729. And that's my answer. The probability that none of 3 cars come from Germany, 72.9%. All right, this is the one that drives all my students crazy. It's the at least questions. At least one of the 3 cars is US made. Well, if you have at least one friend on Facebook, it means you could have more. This could be 1 car is from the US, or 2 cars, or 3 cars. Ooh, that's a lot of ors. That would be doing a lot of adding. Not to mention, if it's 1 car from the US, right, if I make a little box, it could be this car, could be this car, could be this car. I'm going to end up with a lot of options, and this problem is going to get really complicated really fast. So I'm going to show you my shortcut. There's 3 cars, so I could get 1 or 2 or 3 from the US. But there's a number I didn't list here, something that I don't want. I do not want 0 cars from the US. Aha, things that are not. I can use the complement rule. I can figure out the probability, excuse me, let's not highlight that not. I could figure out the probability 0 cars are US made, and then, using the complement rule, get the not piece. So I'm going to go ahead and do that. Let's figure out the probability I have 0 of 3 cars from the US. Okay, this is going to be similar to the one we just did. None of 3 cars come from Germany. So I've got 3 cars. The first one is not from the US, and the second one is not from the US, because remember I'm going for 0 of 3 from the US, and not from the US. Well, US is 40%, so not US is going to be 0.6, and means multiply, and means multiply. So I put all these together and I get 0.216. This is probably I get 0 US made cars. But that wasn't what I asked for in the beginning. I said, well, I do want US made cars. I want 1 US made car or 2 or 3. So what I have here, this 0.216, this is the piece I don't want. Right? This is the piece I don't want. So I'm going to use my complement rule. My total probability is 1. I'm going to take away the piece I don't want, and that gives me 0.784. That's what I do want. So the probability I get 1 or 2 or 3 US made cars is 0.784. Again, I know these are like, these are going to be your least favorite questions if I had to guess. So we'll check out another one of those. All right, the first Japanese car you see is the 4th one you choose. Whoa, what is that? The first Japanese car you see is the 4th one you choose. Well, okay, apparently I'm going to choose 4 cars. 1, 2, 3, 4. And I like to put ands between, because that's what I'm doing here. I have multiple cars. So the first Japanese car I see is the 4th one. So this last fourth car is going to be Japanese. That means this first car, well, it can't be Japanese because this is the first Japanese car I see. So this first car is not a Japanese car. The second one is still not a Japanese car. And the third one is still not a Japanese car. So now all I have to do is fill in some numbers. Remember that and means multiply. So really, what I'm doing here is I'm actually taking the probability of each of these statements. Okay, I just write it a little shorthand. So the probability I select a car that is not Japanese, well, 30% are, so that means 70% are not. So this is 0.7 times 0.7 times 0.7, right, because I've got 3 that are not Japanese. And then the fourth one, it is. I saw my first Japanese car on the fourth car. So if I plug all that in my calculator, I get 0.1029. So a little over, just a titch over 10%. All right, let's go ahead and look at just a couple more. So we're going now to our story problem about the blood types. We have 45% have type O, 40% have type A, 11% have type B, and we calculated last time the rest have type AB, that was 4%. And now we're going to be choosing 4 donors. So all of these story problems are going to be about 4 people. So number 1, what's the chance we get all of them to be type O? Well, remember, we're choosing 4 people, the first one and the second one and the third one and the fourth one. And I want them to all be type O. So this is really a probability I choose O, probability I choose O, probability I choose O, probability I choose O. Well, type O was 45%, 0.45. And rather than write that times 0.45 over and over again, that's 0.45 to the 4th power. And I'm going to have to round that off just a little bit. I get 0.041 when I put that in my calculator. All right, number 2, they are not all type A. Here's a clue word, not all type A. Not, clue that I'm going to use my complement rule. So I'm going to take 1 minus, and I'm going to take away the probability that they are all type A, because that's the not piece. All right, so all type A, well, there's 4 of them, so it would have to be type A, and type A, and type A, and type A. So I'm going to get 4 type A's. So this is 1 minus, I'm going to put this in brackets here. Well, choosing a type A person was 0.4, so this is going to be 0.4 to the 4th power. That's 1 minus 0.0256. That gives me 0.9744. All right. I'm going to ask you to try number 3, where we have no one is type AB. Think about what that would mean. And then number 4, at least one person is type B. I want to help you get started on this, but you might want to go back to that example we did. At least one is type B. At least one means 1 person or 2 people could be type B, or 3 people could be type B, or 4 people could be type B. Yikes. That's going to be really complicated. So instead, I'm going to focus on what we don't want. At least one is type B means I do not want the situation where I have 0 type B people. So if I can figure out what's the chance I have 0 type B people, I can use my complement rule. All right, so 0 type B people. I'm going to do 1 minus the probability I get 0 type B people. It's going to be 1 minus probability. Let's put this in big brackets here. 0 type B, that means this person is not type B, and the next person is not type B, and the next person is not type B, and the next person is not type B. Think about that and see what you can come up with.